In this video, we're going to go over some practice problems from our textbook from chapters 5 and 6, starting with section 5.4 here. So this section is on conditional probability and the general multiplication rule. So let's get started with question 18 here. We're told that adult Americans were asked whether they use social media regularly, and the following table is based on the results of the survey. So we have our two categories here, the age range, and then whether or not these people use social media. So for part A, we want to figure out the probability that a randomly selected adult American used social media given the individual is in this age group. So we're looking at conditional probability here. We want to find the probability of this guy given this one. So I actually have the formula pasted here for conditional probability. This is the conditional probability rule for two events E and F. So the probability of event F given event E is given by this guy here, where we're going to look at the probability of event E and F occurring divided by the probability of event E. Another way to think of this is the number of outcomes in events E and F divided by the number of outcomes in event E. So using this rule here, we want to find the probability that a randomly selected adult American uses social media. So that's going to be our event F is social media, given our event E in this case. So we're going to have this line here is this age group. So we're going to use this formula here. We want to find the number of outcomes or the number of people that use social media and are in this age range. So we're kind of thinking of this as this guy, the number of outcomes in event E and F. And then we're going to divide this by the number of outcomes in event E, so the amount of people that are in this age range. All right, so referring to this table here, we can determine these values. So the number of people who use social media and are in this age range can be found by this guy here. So that'll be 117. And the number of people in this age group is going to be this total here, this 150. All right, so dividing those guys, this is going to give us 0.78. So that'll be our probability that a randomly selected adult American uses social media, given that person is in the 18 to 34 age range. Now for part B, what is the probability that a randomly selected adult American is in this age range, given the individual used social media? So in this case, our events E and F are going to be swapped. So we want to find the probability that a randomly selected adult American is in this age group, given they use social media. So again, we're going to use this formula here where we're looking at the number of people in this age group and use social media. And then we're going to divide this by the number of people who use social media in total. In this case, remember our events E and F are swapped from part A. So the number of people who are in this age range and use social media is going to be the same that we saw in part A here. That's going to be this 117. But our total in this denominator here is going to be different. We're looking at the total number of people who use social media. So we're going to look at this column here in this table and look at this total. So it's going to be 338. Dividing these guys, we're going to get approximately 0.346 as our conditional probability. Now for this next problem, we're going to be using our general multiplication rule. For 24 here, suppose that two cards are randomly selected from a standard 52 card deck. So for part A, what is the probability that the first card is a club and the second card is a club if the sampling is done without replacement? So this means when we pull the card, we're not going to put it back into the deck. So our general multiplication rule is pasted here. So this is the probability that event E and F occurs. It's going to be given by the probability that event E occurs times the probability that event F occurs given the occurrence of event E. So we have our conditional probability here. So in this case, we want to find the probability that the first card is a club. So that's going to be event E. And the probability that the second is a club. So that'll be event F. So this is going to be given by the probability of event E, the first card being a club, times the probability that the second card is a club, given the first card is a club. All right, so we need to find the probability of event E. Well, in a standard 52 card deck, we know that there's four suits, one of them being clubs, and in that suit, there are 13 cards total. So we know that there are 13 clubs. So the probability that the first card we pull is going to be a club is going to be 13 out of the total amount of cards in this deck, which we know to be 52. So that's the probability of event E occurring, this first card being a club. Now we need to multiply this by this probability here, the probability that the second card is a club given the first was a club. Now we have to be careful of the wording here because remember we're doing the sampling without replacement. So when we pull this club out, we're not putting it back into the deck. So that means out of the 52 card deck, there's going to be 51 remaining. And if the first card is a club, then that means there's only going to be 12 clubs remaining in the deck. So the probability that the second is a club, given we already pulled that first one out and that was a club, is going to be the 12 remaining clubs out of the 51 remaining cards in the deck. So this is going to be approximately, or I guess this will be the same thing as 1 over 17. And this is going to be approximately 0.059. So that would be the probability in this case. Now for part B, we want to find the probability that the first and second card is a club if in this case the sampling is done with replacement. So as soon as we pull that club, we are just going to put it right back into the deck. So again, we want to find the probability that the first is a club and the second card is a club. So again, this is going to be the probability that the first is a club times the probability that the second is one, given the first was a club. Okay, so we have the same formula here, but the probabilities are going to be different since we're doing replacement with the sampling in this case. So again, the probability that the first card is going to be a club is just going to be the same, the 13 clubs out of the 52 card deck. Now, for this next one here, this conditional probability, we want to find the probability that the second card is a club given the first was a club. But in this case, we're putting this club right back into our deck as soon as we pull it. So that means there's still going to be 13 clubs and there's still going to be 52 cards in total. So this will be the probability that the second is a club given the first one is after we replace it. This is going to give us 1 out of 16, which is going to be equal to 0.0625. This brings us to section 5.5, where we're looking at counting techniques. So for question 48 here, four members from a 50-person committee are to be selected randomly to serve as chairperson, vice chairperson, secretary, and treasurer. So the first person selected will be the chairperson, the second the vice, the third the secretary, and the fourth the treasurer. So we want to figure out how many different leadership structures are possible. Now notice in the structure of this question, we know that the order of selection determines the office of the member. So the first person selected is the chairperson, the second is the vice chairperson, and so on. So in this case, order does matter. So we're looking at a permutation. So we're going to use the permutation formula, which is NPR here. And so what's happening here is that we have n distinct objects and we're picking R of them. So that's kind of how I like to think of it in this case. So this formula is given by n factorial divided by n minus r factorial. So we're just going to plug in the known information. We know that there are 50 distinct objects or 50 people. So we're going to have 50 factorial on the top here. Then we're going to have 50. And remember, we're picking four members to be the chairperson, vice chairperson, and so on. So this is going to be 4 for our R. Okay. So this is going to be the same thing as 50 factorial divided by 46 factorial. So this is going to be the same thing as, one way to think of this is we're going to have 50 times 49 times 48 times 47 all the way up to 1 in this case. And in the denominator, we're going to have 46 to 45, again, all the way up to 1. So what we can do is we can figure out what this number is and then divide it by this number, or we can recognize that everything past this 47 here is pretty much everything, or it is exactly everything that we have in our denominator. We're going to have multiplication by 46, 45, 44, all the way up to 1. So everything in this region cancels with everything in the denominator here. So these guys are all going to cancel and these guys all cancel. So what we're left with in this case is just going to be the multiplication of 50 times 49 times 48 times 47. So just to emphasize this, and this is going to give us this big number here. All right, so this tells us that there's going to be 5,527 and 200 different leadership structures possible for this committee. Okay, so for the next question, for 54 here, we're told that a family has 8 children. If this family has exactly 3 boys, how many different birth and gender orders are possible? Now, notice in this case, there are 8 children, and we need to determine the number of ways 3 can be boys. So in this case, the order of the 3 boys does not matter. We just want to have 3 of them. So we're looking at a combination problem. Order does not matter in this case, and this kind of problem is denoted like this here. Now, in this case, I kind of think of this as in choose R. So we have indistinct objects and we're choosing R of them, but the formula is slightly different from our permutation formula. We're still going to have the n factorial on the top here, and in the bottom, we're going to have R factorial times this guy. Okay, so we can just plug in our known information. So there's going to be 8 distinct objects or 8 children. So we're going to have 8 factorial in the numerator. Now in the denominator, we're choosing 3 of them to be boys. So our R is going to be 3. So we're going to have 3 factorial multiplying 8 minus 3 factorial here. Okay, so let's see what we're left with. Just simplifying this, we're still going to have that 8 factorial on the top. Then we're going to have 3 factorial times 5 factorial. Okay, now in the top here, we're going to end up with 8 times 7 times 6. Just writing everything out here. And then in our denominator, we're going to have 3 times 2 times 1. That's going to be 3 factorial times 5 times 4 times 3 times 2 times 1. Just since we have smaller numbers here, I can kind of show you exactly what's happening in our numerator and denominators, and then we can cancel them just like we saw in the last problem. So notice we're going to have 5, 4, 3, 2, 1 here and here. And so we're just going to be left with 8 times 7 times 6 and 3 times 2 times 1 in the numerators and the denominator respectively. So this is going to give us 56. So this means there's 56 ways to select 3 of the 8 children to be boys. And so there's 56 different, birth and gender orders that are possible. All right, so in section 5.6, we're looking at simulating probability experiments. So that's exactly what we're going to do in this problem here. We're looking at a simulation of the birthday problem. So the problem deals with determining the likelihood that at least 2 people share the same birthday in a room of n individuals. So we have this data file here, and when you click on this link, make sure you are logged into MLM. But the data file represents simulated birth dates of 15 individuals, repeated 2,000 times. So each birth date was assigned a number from 1 being January 1st to the last day of the year being December 31st. So for part A, what is the birth date of the randomly selected individual in row 1, column 1? And did the first simulation result in at least 2 people sharing the same birth date? So we're going to have to click on this link here. It's going to bring us to StatCrunch. Now, the randomly selected individual in row 1, column 1 is going to be 250. So this person has a birth date on day 250 of the year. Now, the second question is, did this first simulation result in at least 2 people sharing the same birth date? So notice the first column here is the amount of rows that we have, and that's the amount of times that the simulation is repeated. So we're going to have 2,000 rows. And then looking at each column here, we have B day 1 through 15. So these are the 15 people in this first row here, and it has all of the days of, or all of their birth dates. Now, in the last two columns, we have same birthday here. And in this first row, notice how it says no match. And actually, rows 1 through 8, it says no match, meaning that no two people have the same exact birth date in the first 8 simulations or 8 rows here. However, notice in rows 9 and 10, we do have a match. So this means at least two people share the same birthday. Okay, so that's what's happening in this file here. So going back to our problems here, the birthday of the randomly selected individual in row 1, column 1, we saw was day 250. Now, assuming it's not a leap year, this is going to be September 7th. And so assuming it's not a leap year. And then to answer the second question, the first simulation did not result in two people sharing the same birthday. So we'll say the first simulation, also known as row 1, does not have another 250 for the remaining individuals. So the first simulation did not result in at least two people sharing the same birthday. Okay, now for part B, based on the simulation, what is the probability that at least two people will share the same birth date? So let's go back to this file. So we want to find the probability that at least two people will share the same birthday. Well, we need to figure out how many simulations resulted in at least two people sharing the same birthday. Essentially, we need to figure out how many of these rows have or say match in this last column here. Now, what you could do is you could manually count that 2,000 times, or what we can do is find wherever it says a match in this column. So we're going to go to data. I clicked on that data menu. Then we're going to go to row selection and then find here. Now, what we want to do is we want to find the word match in the particular column that has it, which would be the same column. Okay, once we enter all of that information, we're going to press find in the up or find in the up right corner here. And notice it says found this match word in 503 cells in that same column. So this means 503 simulations resulted in at least two people sharing the same birthday. So with this information, we can go back to our file and notice that they're also going to be highlighted, which is nice. And then in the bottom left corner, it also tells us how many rows, 503 rows. I hope you can see that. It might be cut off. But going back to our problem here, based on this simulation, what is the probability that at least two people will share the same birthday? So the probability that two, we'll say at least two people share the same birthday. Well, we know that we saw 503 simulations resulted in at least two people sharing the same birthday out of the 2,000 simulations that we had. So this is going to be 0.2515, or we can say that 25% of people in this simulation resulted in at least two people sharing a birthday in a group of 15 individuals. So the probability 25% that at least two people share a birthday in a group of, in this case, it was 15 individuals. Next, in section 6.1, we're looking at discrete random variables. So for question 20 here, a Wendy's manager performed a study to determine a probability distribution for the number of people given by our random variable x waiting in line during lunch. So the results are given here. And for part A, we want to verify that this is in fact a probability distribution. So there are two things that we need to check to verify this. The first is that all of Our probabilities are in between 0 and 1, and this is inclusive. Right, so looking at all of our probabilities here, we can see that every single one is in fact between 0 and 1. So our first condition is met. Our second condition is that the sum, so we're going to use our summation notation of all of our probabilities is going to be equal to 1. And we can check this by adding all of our probabilities together, starting with the first one, moving on to the second, and then continuing this process all the way up to the last probability here. Adding these guys together, we will get that this is equal to 1. So, and you guys can check that. So our second requirement here is met. So this is a discrete probability distribution. So we'll say that here. All right. Now for part B, what we want to do is compute and interpret the mean of our random variable x. So the mean of this guy, which is going to be denoted as mu, and then we have our random variable x here, is going to be equal to this here. Okay, so this is going to be the sum of the products of our value of our discrete random variable and the corresponding probability. So in order to find this, we're going to take our first value, which is 0, multiply it by that probability. Take our second value, which is 1, multiply it by that probability, and then repeat this process here. Okay. So doing so all the way up to our last, we have 12 is the value of our random variable, looking back at this table, and the corresponding probability is 0.006. Okay. So adding all of these products together, we're going to get that this is equal to 4.87. So this is our mean, and we also want to interpret it. So this means that, let's see, the average number of people waiting in line is observed to be about 5 people. So we'll write that here. Oh, so roughly, write this nicer, 5 people. Just rounding up there. And then for part C, we want to compute our standard deviation. So we have a formula for this as well. We're going to have this guy representing our standard deviation, and it's going to be given by, we're going to take the sum of, we have our brackets here. We're going to have our value, and then we're going to subtract out our mean, and we're going to square that for each other value for our random variable. Then we're going to multiply this by the corresponding probability. So we're going to take the sum of all of these guys, and whatever value that is, we're going to square root it. Okay, so what we can do is, just so we have enough space, we are going to take the square root. Let's start with the first one here. So our first value is going to be 0. Looking back at this table, our first value for our discrete random variable is 0. And then our mean was 4.87. We're going to square this and multiply by the corresponding probability, which was 0.011. And that's just our first one that we're looking at. We're taking the sum of all of these guys. So next we have to go to our next value, which was 1, subtract out our mean of 4.87, square that, and then multiply by the corresponding probability, which is 0.035. All right, and we're going to repeat this process all the way up to our last value, which we know was 12. We're going to subtract out this mean, square it, and then multiply it by the corresponding probability for our value of 12. So this will be 0.006. And then whatever this is, we do need to take the square root of this entire thing here. All right, so doing so, This is going to be approximately the square root of 4.969. Taking the square root of this is going to give us 2.229. Okay, so roughly 2.2 people. All right. Now for part D, what is the probability that 8 people are waiting in line for lunch? This one's fairly easy. We're just going to go back up to this table here. We're looking at our value of 8 for a random variable. This probability is going to be 0.063. So we'll say the probability that 8 people are waiting in line is 0.063. And then lastly, for this problem, what is the probability that 10 or more people are waiting in line for lunch? So 10 or more, we're going to denote this, the probability that our random variable is greater than or equal to 10, since we're looking at 10 or more. So this is the same thing as the probability that 10 people are in line, or 11 people, or 12 people. And that's our maximum value, so we're not going to go higher than that. So in order to find this, we know from our last video, I believe, that this is going to be, or our last section, this is going to be the probability that 10 people are waiting in line plus the probability that 11 plus the probability that 12 people are waiting in line. And we can find this just by going back up to this table here. So we're going to take the probability of 10 people, 0.019, plus this one for 11 and 12 people. All right, and so this is going to give us 0.029. Okay, now notice this is a very small probability. But remember, this is the probability that 10 or more people are waiting in line for lunch. And since this is pretty small, we would actually consider this to be somewhat unusual. All right, so this brings us to our next question. For 24 here, the graph of the discrete probability distribution represents the number of rooms in rented housing units in 2017. So we have our number of rooms along our horizontal axis and the probability on our vertical axis here. So for part A, what is the probability that a randomly selected rental unit has 5 rooms? So we're just going to look at this graph here. Looking at the number of rooms being 5 here, we get 0.198. So the probability that a randomly selected rental unit has 5 rooms is given by 0.198. All right, fairly simple. Let's look at part B. What is the probability that a randomly selected rental unit has 5 or 6 rooms? So the probability of 5 or 6 rooms is going to be given by the sum of the probability of 5 and 6 rooms. Yep. So we've seen this in past problems here. So we know that the probability of a randomly selected rental unit having 5 rooms is 0.198 from part A. And then for 6 rooms, that probability is going to be 0.103. Adding these guys together here, we're going to get a probability of 0.301. So also fairly straightforward. Part C is similar. What is the probability that a randomly selected rental unit has 7 or more rooms? So in this case, the probability that our randomly selected rental unit given by the discrete random variable x is greater than or equal to 7. We saw this in the last problem. This is going to be the probability of 7 plus the probability of 8 plus the probability of 9. And that's our highest amount of rooms there. So we're going to add these probabilities together from our graph. We're going to get 0.039 plus 0.018 plus 0.008. Adding these guys together, we're going to get a probability of 0.065. And then lastly, for this problem, if a rental unit is randomly selected, how many rooms would you expect the unit to have? And we have this keyword expect here. Now, if you looked through the book in this section, we know that because the mean of a random variable represents what we would expect to happen in the long run, it's also called our expected value, which we denote as E of x. So our expected value of our discrete random variable x is given by the mean of this discrete random variable. And we know that this is going to be the sum of the product of our value of that random variable times the corresponding probability. So, for example, go back up to our graph here. If we're looking at the value of our discrete random variable being 1, in this case, 1 room, we're going to multiply that by the probability of 0.009. So that'll be our first product. And remember, we're taking the sum of all of these guys. So that means we're going to have to add this to our second value of our discrete random variable, which is 2 rooms, and multiply that by the corresponding probability. And we're going to repeat this for all 9 rooms. So 2 rooms, we have a probability of 0.017. We're going to do this all the way up to our last room, which has a probability, or our last number of rooms, which has a probability of 0.008. So this is going to give us 4.355. So we would expect the unit to have about, rounding up, 4.4 rooms on average. All right, so this brings us to section 6.2, where we're looking at the binomial probability distribution. So for question 34 here, we're given that n is equal to 9 and p is equal to 0.8. And first, what we want to do is construct a binomial probability distribution. So let's do that first. And we're able to do that with this formula that I have pasted here on the left. Remember, this is going to be the formula for the probability of obtaining x successes in n independent trials of a binomial experiment. So in this case, we're going to have 9 independent trials, and P is going to be the probability of our success. So what we need to do is find the probability of x successes for x equaling 0 all the way up to 9 here. So we're going to start with x is equal to 0. We want to find the probability that x is equal to 0. It's going to be given by this here. So we're just plugging in our known information and simplifying. So we know that this is our combination. We're going to have 9 choose 0. So we have 9 trials and we're going to choose 0 of them essentially. So this is going to be given by 9 factorial on the top. Then we're going to have 0 factorial times 9 minus 0 factorial there. Then we know 0.8, or actually anything raised to the 0 power, is just going to give us 1. So we're just going to leave that as is. And then we have 1 minus 0.8 raised to the 9th power. So this is going to be 0.2 raised to the 9th power. All right. Now from here, something that we need to note is that 0 factorial is equal to 1. Okay? So in this case, what we're going to end up with is we have 9 factorial in the numerator, 0 factorial in the denominator times 9 factorial. So these guys are actually going to cancel out, and we're just left with 1 over 0 factorial, which gives us 1. You can kind of think of it like we have 9 choose 0, and that equals 1 because there's only one way to have 0 successes out of the 9 independent trials. So this guy, we still have 0.2 raised to the 9th power. But we're just going to end up with 1, since 0 factorial is given by 1, times 0.2 raised to the 9th power, which if we were to put this into our calculator, we're going to end up with 0. We got a bunch of zeros here, 512. Okay. Now we're going to repeat this process for every single value of x, for every possibility of success here. So our next one is going to be given by x is equal to 1. We're going to end up with this here, which we're going to plug directly into this formula. We're again going to have 9 factorial in the numerator for this guy. Then we're going to have 1 factorial times 9 minus 1 factorial. Then we're going to have 0.8 raised to the first power, which is just 0.8. And then we're going to have 0.2 raised to the 8th power. Okay. Repeating this process for x is equal to 0 all the way up to x is equal to 9, we can create our binomial probability distribution. So in the interest of time, I'm going to go ahead and do exactly this that we saw for x is equal to 0 for the rest of our possibilities of successes here. And then I'm going to put that into a table. Okay, so we have the probability of having 0 successes given by, we're going to round this to 0. The probability of having one success, we're also going to round to zero, and we repeat this all the way up to the probability of having nine successes, which we're going to round to 0.1342. So putting this into a table, we have our binomial probability distribution. So of zero success, our probability is zero. Of one success, our probability is zero. Repeating this all the way up to having nine successes, our probability is given by 0.1342. Now, for part B of this problem, we want to compute the mean and standard deviation of the random variable using methods from section 6.1. So we know what that looks like. We have these formulas here from section 6.1. If we want to find this mean, we're going to take the sum of all of these products. So we're first going to have zero as zero successes times that corresponding probability, which is just zero. Then we're going to add one success multiplying by that probability, which is zero, two successes multiplying by that probability, which is 0.003, all the way up to nine successes multiplying that by that probability. Okay. Doing so, we're going to get that the mean is about 7.2. Okay. Now, doing something similar for our standard deviation here, we're going to take the square root of this thing. So taking the square root of the sum of, first we're going to take our x being zero, so having zero successes, and subtract out the mean. We're going to square that and multiply by the probability, which is zero. So we're going to do this all the way up to x equal to 9, so we have 9 successes. Subtracting out the mean, squaring that, and multiplying by the corresponding probability. Once we take this sum here, this whole thing is a sum, we're going to take the square root of this. So let's see, before we square root this, this is going to be 1.4400 approximately. Taking the square root of that is going to give us a standard deviation of 1.2. Now for part C, we want to do the same thing, but we're going to compute these values using the methods from this section. So we're going to use the formulas introduced in this section. From section 6.2, we're going to see that the mean is going to be the same thing as the number of trials times the probability. So we know that there are 9 independent trials, and we know that the probability of success is going to be 0.8. So multiplying these guys together, we are going to get 7.2, which is the mean that we saw from using methods in section 6.1 here. Now the formula for our standard deviation in this section here is given by, we're again taking the square root of something, and it's going to be this product here. So we're going to plug in these values. This is going to give us, again, 1.2, which is the standard deviation that we saw using the methods that we saw in 6.1. And then lastly, for part D, we want to draw a graph of the probability distribution and comment on its shape. So I'm just going to go ahead and paste the graph here from the solutions just in the interest of time. All right, so I pasted the graph here. On our horizontal axis, we have the number of successes in our 9 independent trials. And on the vertical axis, we have our probabilities. So we know from our table here that the probability of having 0 success is 0. Similarly, for the probability of having 1 success. And then notice here, the probability of having 7 and 8 successes is given by approximately 0.3. Going back to this graph, we see 0 probability for these guys, and notice the probability is 0.3 for 7 and 8 successes here. So this graph accurately represents our binomial probability distribution that we created in part A. And then lastly, as we can see, this distribution is going to be skewed left. So we'll write that here. So our distribution is skewed left. All right, so from here, we just have one more problem. So for question 38, Clarinex D is a medication whose purpose is to reduce the symptoms associated with a variety of allergies. In clinical trials of Clarinex D, 5% of the patients in the study experienced insomnia as a side effect. So a random sample of 20 users obtained, and the number of patients who experience insomnia is reported. So for part A, find the probability that exactly three experience insomnia as a side effect. So before we do that, let's just note some things from the problem statement here. We have a random sample of 20 users. So this tells us that N is going to be 20. And then we saw that 5% of the patients experience this insomnia that we're looking for. So the probability in this case is going to be 5% or 0.05. So with this information, we can use the formula that we saw in the last example, our binomial probability formula, to find the probability that exactly three experience insomnia as a side effect. So we have 20, we're choosing three for the success of experiencing insomnia. Then we're going to multiply this by the probability raised to the third power here, and then multiply that by 1 minus this p-value raised to the n minus x here. So in this case, 20 minus 3. We're going to have 20 factorial here, 3 factorial times 20 minus 3 factorial in the denominator, 0.05 cubed times 0.95 raised to the 17th power. All right, so this is going to give us, let's see, we're going to have this value times, we still have this 0.05 cubed, so just simplifying certain things here. And then this guy raised to the 17th power, plugging all of this into our calculator, we're going to get 0.0596. So this means in a random sample of 20 of these Clarinex D users, there's a probability of 0.0596 that exactly three will experience insomnia as a side effect. Now for part B, in this case, we want to find the probability that three or fewer experience insomnia as a side effect. So we want to find the probability that x is less than or equal to 3 in this case. Now, in order to do that, we're going to use the facts that we're looking at, the probability of 0 plus the probability of 1 plus the probability of 2 plus the probability of 3 people experiencing insomnia as a side effect. So in order to do so, we're going to have to use this formula that we saw in part A here for all of these probabilities. Now, I'm not going to do that in the interest of time here, but we're just going to plug x is equal to 0 into this formula everywhere where we have an x. So this would be a 0, this would be a 0, and that would be a 0. We'd repeat this process for 1, 2, and then we already know what the value is for 3. Doing so, we're going to get 0.3585 plus this guy plus, and then finally the probability of 3 users experiencing insomnia. Adding these guys together, this is going to be 0.9842. Yeah. So we would expect that in a random sample of 20 of these Clarinex D users, there's a probability of 0.9842 that no more than 3 will have insomnia as a side effect. Okay, let's look at part C. This is kind of similar. We want to find the probability that between 1 and 4 patients inclusive experience insomnia as a side effect. So we're looking for this probability here. And this is inclusive in this case because we're including the probability that one person experiences insomnia as a side effect and that 4 people might experience insomnia as a side effect. So in this case, we're going to do something similar to what we did in the last example. We just want to add all of these probabilities together. And we're going to find them exactly like how we did in parts A and B. So the probability that one user is going to experience insomnia is going to be given by 0.3774, like we saw in part B. The probability that two might is 0.1887, and then so on. All right, so the probability that between 1 and 4 patients inclusive might experience insomnia is going to be given by 0.6389. And then lastly, would it be unusual to find 4 or more patients who experience insomnia as a side effect? So in this case, we're looking for this probability. The probability that 4 or more, so we have inclusivity in this case as well, experience insomnia as a side effect. So we could use the same methods that we saw in parts B through C here, where we're just going to take the sum of all of these probabilities. But in that case, we'd have to find the probability that 4, 5, 6, all the way up to 20 patients experience insomnia and add them together. So that is a lot of work. Instead, what we could do is we could use our complement rule. So the probability that 4 or more patients experience this side effect is going to be the same thing as taking the entire probability, so 1, and subtracting out the probability that less than 4 patients experience insomnia as a side effect. And notice that this is going to be the same thing as 1 minus the probability that 3 or fewer experience insomnia as a side effect, which is exactly what we calculated in part B here. So this is just going to end up being 1 minus the 0.9842. All right, subtracting these guys, we're going to get 0.0158. So there's a probability of 0.0158 that 4 or more in a sample of 20 patients would experience this insomnia as a side effect. And lastly, we would say this is unusual since the probability is less than 0.05. So this would be unusual since the probability of this happening, of 4 or more patients experiencing insomnia as a side effect, is less than 0.05. All right, so that's it for this video.